前天啊，有几位同学到我的办公室送了我一盆红的花，很漂亮的。我问他们说这是你们几个人送的还是全班送的？他们是说是全班送的，所以我要谢谢全班。那么后来我跟他们几位谈了谈，他们希望我在课外能够有机会跟大家再接触一下子，所以我想我选2个时间，我要跟阮教授还有安教授谈谈是什么时候最合适，给大家2个课外的演讲，这是什么时候？等到我们安排好了，就会告诉大家。另外，我问了他们几位，他是不是进不来？另外，我问了他们几位，说是我讲了有几本书，可以大家课外去看的。他们说那个有个问题，因为那些书可以借出去，你去的话120个人，很多别的同学已经把它借出去了，所以一时看不着。那我想这一个补救的办法就是我再多写几本，那么多写几本，你们就也许有的可以看着。我现在稍微介绍一下，这第一本是 C. Gray， 他写了一本书，这书的整个的名字我不完全清楚，From Falling Bodies etc. 这个书学校有，学校图书馆有，我不记得是翻译的还是原文的。C. Gray 是一个重要的物理学家，他比我大概大差不多20岁的样子。那么他是在30年代的时候追随 Fermi，Enrico Fermi 是20世纪最伟大的物理学家之一。那么 Fermi 那个时候，因为在 Fermi 以前，意大利的物理并不特别行。那么就是 Fermi 带了几个人，他们在30年代做了一系列的实验，是非常重要。这些实验叫做 slow neutron， 慢的中子，慢的中子引起核反应是非常容易。那么这个是他们的一个大发现。那么 C. Gray was one of the group of Fermi's group， and 那我可以讲一个很重要的一个故事，这本书里头有没有这个故事我不知道。他那时候在意大利，a professor of physics in Italy is appointed by the Ministry of Education， 不是像这儿，比如清华大学有个教授是清华大学聘的。他那个是你在美国也是 Stony 教授是 Stony 大学聘的，意大利是所有的意大利的 professors of physics were and still are appointed by the Rome government, and so if there is a vacancy in one of the universities, the ministry will discuss which is the best candidate. So there's a competition all the time, and one of the universities that had a vacancy was Palermo. Palermo is the capital of Sicily. 西西里是个岛，是个很大的岛，是很漂亮的一个地方。可是 Sicily 的大学Palermo 的大学没有名，结果C. Gray was appointed to become a professor at Palermo. He was very disappointed. He spent several years there, and that was a time when he was unhappy. But during that time, he visited Berkeley, California. Berkeley at that time had the world's largest cyclotron. And you know, in a cyclotron, you accelerate particles. And then you use those particles like alpha particle to hit a nucleus, and then there are fragments, and you study the fragments. after you do it for, let's say, 6 months, the body that is hit becomes very radioactive. And in those days, they didn't pay any attention, so they just put it in the corner and put a new target in there. So when Segre visited Berkeley, he found a pile of discarded targets there, and he was very intelligent. He went to Lawrence, who was the director. He said, you have all these used targets. Could I have a piece? Lawrence said, sure. So he took a piece back to Palermo, and there he made an analysis, and he found element 43. If you remember, Mendeleev had this periodic table, and at the beginning of the 20th century, it was filled up, but there were a few vacancies because nobody has found those elements. And Segre went back. Element 43 was not natural. There's no natural substance with 43, but in a cyclotron, it's artificially created, and so he found it. So that was what made him a very distinguished physicist. This is a very interesting story. What it means is that in the frontiers, you have all kinds of opportunities. You have to have a sharp eye. And all these distinguished physicists in Berkeley did not realize that there is something to be found in the pile of used targets. But he had the bright idea. He then went to the United States and did very distinguished work. He was the thesis advisor of Wu Jianxiong. When Wu Jianxiong went to Berkeley to get her PhD, she studied with Segre. And this book was very interesting. I had more or less read it. The next one is E.T. Bell's Man of Mathematics. E.T. Bell was a professor of mathematics in America, and he wrote this book in the 1920s or 30s. It's a collection of some 20 short biographies of great mathematicians. It exerted a profound influence. In fact, it influenced me. When I was a freshman in Xinyan Lianda, my father, who was a professor of mathematics, borrowed from the library this book. So I began to read it, and it talks about great mathematicians and their contributions. I didn't understand most of the contributions, but the stories were very fascinating. Now, the book was not only famous in China, it was famous all over the world. Now I read that there are people who say that this book is not entirely reliable. In other words, what Bell said about some of the mathematicians was not entirely reliable. But nevertheless, it was a very interesting book, and it had a profound influence. In particular, there is a chapter about Hamilton. Hamilton was a great mathematician and physicist. I told you that he invented the quaternion. And that chapter in E.T. Bell's book about Hamilton was called An Irish Tragedy, because Hamilton was from Ireland, and E.T. Bell thought that Hamilton's life was a tragedy because in the latter part of Hamilton's life, after he invented the quaternion, he devoted all his efforts to make quaternion the basic mathematics of physics, but unsuccessful. However, I think E.T. Bell is not quite right. I have the feeling, I think I told you a few times ago, I have the feeling that the quaternion will enter into physics in a major way, but not yet. And that I had written about in my selected papers. If you refer to one of my early lectures, I had said that. The next one is Gamow. Gamow was a distinguished physicist. He was maybe 15 years older than I am. He was a Russian physicist, but he escaped from Stalin's Soviet Union by sailing a boat in the Black Seas, and from there he got to America and he settled in America. He was a physicist and astronomer. He had many important contributions. The most important was he was the one who explained the long lifetime of radioactivity in the late 1920s. Many people believe he should have won a Nobel Prize for that. The reason that he didn't win a Nobel Prize is because there were so many important pieces of work. So there were many candidates for Nobel Prizes in those days. And as a consequence, he never got it. Most people believe, and I subscribe to that theory, if his contribution were moved to today, he would receive a Nobel Prize. He wrote this book in a very humorous way, and it's a very interesting book. It's about special relativity and quantum mechanics. He was a good friend of Edward Teller, my thesis advisor, and he talked in a very loud voice, and there were many stories about him. He likes to drink. He oftentimes gets very drunk. And there's also another thing about him. Namely, you know that with the genetic code, it is 3 units of the DNA that code one protein. And in the 70s, there was a question of how many units. We now know it's 3 units. The question at that time was how many units of the DNA codes one protein. And Gamow speculated it's 3. That turns out to be correct, but the reason was wrong. Now, what was his reason? His reason was a combinatorial statement. He said that if n units code a protein, and one knows there are 4 bases, A, C, T, G. So the question is, if you select n things out of 4 with repetition allowed, what should n be in order that the number of possibilities is 20? Because he knows there are 20 proteins. So the question is, out of n DNA units with the possible repetition of the 4, what is n so that the total number of different choices is 20? Now, that's a combinatorial problem. Go back and think about it. It is 3. So he wrote that the n should be 3. We now know 3 is correct, but it's wrong for 2 reasons. Reason number 1, he did not consider the order of the 3, while the combinatorial problem had no concept about the order of the 3 DNA units. So that's a mistake number 1. Number 2, he thought it's unique that each choice corresponds to 1 protein, and there are 20 proteins. But it turns out that in actual practice, there are several possibilities, ordered triplets, that code the same protein. So he was wrong in two accounts, but the number was correct. This is a well-known story among the biologists. I tell you the story because with a purpose. There is a feeling among the international physicists of exuberance, that you think about all kinds of things and don't be afraid that you make a mistake. And that is characteristic of many physicists, especially Gamow and Teller. But that is different from the lesson that you learn in China. The lesson that you learn in China has a tendency to make you very focused. I've repeatedly said that both have advantages. So do not think that the Western way is necessarily better. But if you are immersed in one system, it is best if you absorb some of the advantages of the other system. Next one is James Watson's Double Helix. This is a very important book. Watson in 1953 with Crick, who recently died, wrote this most important paper about the double helix, which is undoubtedly the greatest paper in science, in biological sciences of the 20th century. And they won the Nobel Prize, I think, in the early 60s. And then later on, he wrote this book, which is a popular book, which described the history of his discovery with Crick. It's a very interesting book because it tells you how young American scientists go about doing their work. They are not learned. They don't study very hard, and they don't know too much. But they are full of enthusiasm and they work very hard and they are not afraid of anything. And that book essentially says such a way could achieve great things. The next one is Abraham Pais, Sutter is the Lord. That is the biography of Einstein. Now, by now, there must be 20 or 30 biographies of Einstein of various kinds. This is absolutely the best. Everybody regards this as the best biography. Abraham Pais was my colleague. 我在Institute for Advanced Study 跟他同事了10几年。He was a distinguished physicist. He made important contributions to physics. But after he was 60 or thereabouts, he started to write books. And the first book that he wrote was this book. And it's a very good biography of Einstein, both in terms of his analysis of Einstein's physics and in terms of his analysis of the personality of Einstein. And this book has been translated a few years ago, and there's a recent revised translation. It's 商务印书馆2004，翻译的人是一位姓方的。I'm pretty sure our library has both the English and the translation. 最后呢，我 recommend 这个 article， 清华大学学报哲学社会科学版，2004年第4期。我 recommend 这个原因是因为 in May of this year， 中文系，清华大学的中文系的老师，请我去跟他们的学生随便谈谈，所以我就去了跟他们谈了1个多钟头，他们记录下来了，然后把它印出来了。你们如果找这个看看的话，至少你对于我一些对于乱七八糟的很多事情的一些想法，你们从这上可以看到。上回我们 一个重要的结果是说 kinetic energy final 减去 kinetic energy initial 是等于的 work done。这个 work 是 on the body dot into dx。我要 emphasize 这是 on the body， 不是这个 body 所做的 work。body 所做的 work is the opposite of this。所以 the work done on the body serves to increase the kinetic energy of the particle。而且我要特别要跟你们讲，这 S dot dx 可以是 negative。假如 F 向这方向走 ，dx 向这方向走，那就是比如说，if a body is moving toward me and I try to oppose it, but the body is still moving towards me, then F and dx are opposite to each other in direction. So cosine of the angle is negative. So the body is, so I'm doing negative work on the body, which means the body's kinetic energy will decrease, which is of course in agreement with our intuition. Notice F dot dx may be negative. 或者 integral 这个 may be negative. Next we move to section 7.4, work done by gravitational force. The work done 是 integral of F gravitational， 是 gravitational force on a body dot dx. But we know what the gravitational force is. Let us take the z-axis to go upwards. Then we know Fg is equal to g times k. K is the unit vector upwards. So minus k is the unit vector downwards. So this is the force. But, so this is equal to minus g times integral k dot dx. Dx is equal to dx dy dz. But k has no x and y component, so this is d equal to dz. Right? So it's equal to minus g times integral of dz, of course, is equal to the final z minus the original z. So if a body is moved upwards, suppose it's this way, then z final is higher than the initial. This is the final, this is the initial. So z final is bigger than initial. So this quantity is negative. That means the gravitational force has done a negative work on it. Now let us write down the theorem. The theorem says kinetic energy final minus kinetic energy initial, that's equal to the work done. So that's equal to minus GF plus right, the left side is the increase of kinetic energy, and that's equal to the work done on the body, which is what we just computed. So now I move this, I get kinetic energy final plus GZ initial, the GZ initial final is equal to kinetic energy initial plus GZ initial. Sorry, I missed an M. The force is equal to minus, there's an M times here. So there's an M here. There's an M here. In other words, this is called total energy. Total energy is equal to kinetic energy plus what is called potential energy. This part is mgz is equal to potential energy. Kinetic energy plus potential energy is called total energy. And this formula merely says total energy is not changed. And that's conservation of energy. This is conservation of energy for this mechanical system. So the net result is that first we introduce a concept with gravitational force. We have a concept of the existing potential energy is equal to mgz. Z is the upward coordinate. You might ask, where do you take the z to be zero? So this potential energy is a relative quantity. You can take any place to be z equal to 0. But of course, your friend may not take the same convention. But it doesn't matter, because once I take the origin of the z-axis, I have to stick with it. And when I use it, I would have conservation of energy. Then if I move that the axis, it balances out on the initial and the final part, so it doesn't matter. So therefore we have a concept of potential energy which is relatively defined, and we have a concept of kinetic energy which is 1/2 mv squared. And the concept of a total energy which is the sum of the two. And the important thing is that that energy is not changed. This is a very important, in principle it is very important, and in practice it helps you to calculate many things very easily, as I'll show you in a few minutes. Let us. I think we have defined the unit of work or energy. If you raise if you have 1 Newton force and go a distance of 1 meter, it's 1 joule. If I have 1 kilogram of matter, I'm sure your book probably weighs almost 1 kilogram. If I raise that book by 1 meter, how many joules is done? It's mgz. So it's 1 times 9.8 times 1. So it's about 10 joules. So 10 joules is not a very large energy. It's a person can raise many kilograms, many meters. So to a human being, a joule is not a very large unit. Any questions about the gravitational potential energy? So if I have a body here, I drop it. At the beginning, it has no kinetic energy. If it's at rest, it has no kinetic energy. But relative to the floor, it has a large potential energy. If I drop it, it hits the floor. And at which point, it has a kinetic energy, it has no more potential energy. So the potential energy is converted into kinetic energy in that process. But after a few seconds, it still rests on the floor. So the kinetic energy becomes zero. The potential energy also becomes zero. So what happened? Is the energy lost? Yes, the mechanical energy is lost. But as we'll learn later, total energy is conserved. What happens is that it becomes hot. If a body drops down, if it would get smashed, it breaks into pieces. But suppose it's a rigid body, it's a piece of iron, it won't break. But what happens is that that kinetic energy is converted into heat. And when people realized about 200 years ago that heat is, if you do how to convert it, is equal to the kinetic energy that's lost, then people realized there's a total energy which is conserved if you include both the mechanical and the heat energy. And that becomes the first law of thermodynamics. Okay, what we have done is in 7.4 is the conservation of energy with a system, with a mechanical system, with the gravity. Now we'll do something about work done on a spring. If you have a body on ice with no friction and you tie it to a spring, in a natural state, we take that to be x equal to 0. You all have the experience. If you pull on it, the spring will try to bring it back. If you compress it, the spring will also resist that. In other words, the spring always tries to restore the position of the body to the original position, to the relaxed position or normal position. So what is the force? This is called Hooke's law. Hooke was a contemporary of Newton. In fact, he was a competitor of Newton. He was a distinguished physicist, but he didn't have the mathematical ability of Newton. So he made good contributions, but of course not the earth-shaking contributions like Newton did. Hooke's law says that the force on the body is equal to minus kx. X is the displacement. If x is positive, that means you are elongating, you are stretching the spring. Then the force on the body is negative, so there's a minus sign. On the other hand, if x is negative, then the force on the body is positive. So that's so both cases you have this formula. This k is called force constant. Now let us apply we have F is equal to minus kx is equal to m times d if I multiply this by I didn't do anything. I merely I rewrote the dt, but that is equal to m times d dt of so it is equal to m v dot so if I integrate both sides, I get So I get 1/2 minus k over 2 times x squared So if I move them together, I get k over 2 x squared plus m over 2 v squared in is equal to the same thing final. So again, I have conservation energy. In this case, I have a spring energy. The spring energy is equal to this. This is the kinetic energy. I now have a potential energy of the spring, and that's equal to k over 2x squared. X is the displacement from the normal position, and the kinetic energy plus this potential energy is a constant, just like the kinetic energy plus the gravitational potential energy is a constant if you only have a gravitational force. If you think about this, you can go through this. If a body is subject to both a gravitational force and a spring, then you have three energies. You have total energy, you have kinetic energy, gravitational energy, and spring energy. And the sum of the three should be a constant. Everybody happy? By the way, how about English? Is everybody happy if I speak 100% in English? Good. So we have now learned that for a mechanical system, actually intuition, you know this, for a system which does not have electricity, does not have chemical reactions, does not have tremendous impact which would create heat, you have a conservation energy, and you add the kinetic energy to various potential energies, you get a conserved system. So let us do a sample problem 7-8. The problem is the following. There is a spring in a relaxed state, and here comes a body which moves with a velocity is equal to 0.5 meters per second. Of course, it would compress the spring, and the spring has a K equal to, the spring is equal to 750 newtons per meter. the spring coefficient. What was it? What did the book call it? Force constant. The force constant, the dimension of the force constant is obviously Newton divided by distance, so it's Newton per meter. The question is, how much does it compress it? So let us use the conservation of energy. Initial energy is equal to kinetic energy, which is 1/2 mv squared plus 0, because x is equal to 0 at the beginning. And final energy is equal to 0. Finally, the body stops, so it's equal to 0 plus 1/2 of k x squared. X is the displacement. So therefore, x squared is equal to mv squared divided by k is equal to, we forgot that m was given is 0.40 kilograms. So this is 0.40 kilograms times k is 750 Newton per meter. V squared is 0.5 squared times meter squared second squared. Is the dimension correct? The Newton per meter is equal to kilogram meter per second squared times divide by meter. So meter squared divided by meter squared, kilogram. Is that correct? Something's wrong. Newton per meter. Newton is kilogram times acceleration, m times meter squared. That's correct. Divided by meter. Something's wrong. Does anybody know what's wrong? Let me see. This is v squared, mv squared. M is here, v squared is here. That's correct. Divided by k is Newton per meter. That's correct. And Newton is kilogram times acceleration. That's correct. Divide by meter. Oh, correct. There's nothing wrong. So this s squared cancels this s squared. This meter cancels this. So this gets we get 0.40 times 0.5 squared times 750 meters squared. And if you compute that, you get x. X turns out to be 1.2 centimeters. You can, of course, also do this by integrating the equation of motion. In other words, you can trace how as time goes on, how the particle, how the body is slowed down. But that's much more complicated. In general, when you talk about a motion like this, if you write it down as a differential equation, the energy equation has only time derivative in it, right? The energy equation has 1/2 of mv squared. Mv squared is a time derivative. But the force equation has the second derivative. Energy equation has ddt in it. Force equation has d squared dt in it. In other words, the energy equation is an integrated force equation. In fact, that's how we got it. The way we got those conservation laws were always you write down the force equation and integrate dt, and you get the energy equation. So the energy equation is always the integral of the force equation, which therefore is one step closer to answer. So energy equation is the integrated form of the force equation. So if you can use the energy equation, it's always simpler. You have already done the integration once. Next, we talk about power. We have talked about work. Work is related to the increase of kinetic energy. Now you can feed. If I try to stop something, I do some negative work on it, or the body does some work on me, and there's a rate of work. So power is defined to be the rate of work done. It could be positive or negative. So it is equal to F dot dx dt. So what is its dimension? Its unit. Unit of power. It's called watt. It's equal to joule per second. W is in units of joule. Joule per second. It's also in terms of Newton. Newton times meter per second. Newton times velocity. And it's called a watt. Now, watt is something that we are very familiar with because we have a bulb which is 50 watts, or you have a burner in the kitchen which is say 1,000 watts. We have oftentimes a unit of kilowatt hour. If you pay your electricity bill, you know the kilowatt watt 叫1度，这中国叫1度，就是1个 kilowatt hour。所以你知道1个 kilowatt hour， 我不知道北京kilowatt hour 是什么价钱。A kilowatt hour in America is typically 10 US cents, 1/10 of a dollar. In other words, if you burn a 100 watt bulb 10 hours, you have 1 kilowatt hour, and in America you would pay about 10 cents. I think in China is lower. This is actually a very important issue. How much China charges energy, and because that determines in some sense, the rate of expansion of Chinese business. If the Chinese government wants to deflate, wants to have fewer economic activities, one of the things that the Chinese government could do is to raise the price of electricity. If they raise the price of electricity, then everybody has to be more careful, including the manufacturers. And so that's a very efficient way of deflating, but because of that, it's very powerful economic policy. So therefore, one should use it with great care. 1 kilowatt hour is equal to 10 to the third watts times 3600 seconds. So it's 3.6 times 10 to the 6th joules. That again shows that joule is a rather small unit. A kilowatt hour is the kind of energy that we oftentimes use, and it's equal to almost 4 million joules. In the old days, one sometimes uses horsepower. 1 horsepower today is defined to be 746 watts. Let's do some exercises. Let's take chapter 7, question 11. There's this diagram. There is a frictionless surface on which rests the body, and the body is tied to 2 springs, one on each side. But when in this position, the two springs are both at rest, no forces. The problem is to ask, what happens if I move this by x? What is the force on it? It's a trivial problem. If x is positive, then minus kx is the force on the first of the spring on the right. So you get force is equal to minus kx because of the spring on the right. The spring on the left, the force is also minus kx. So it's equal to minus 2kx. And that's true if k is negative, if x is negative. Right? If x is negative, both springs want to pull it back this way. So you get the minus 2kx, which is positive. B. What is the energy, where each spring has an energy of 1/2 kx squared. So energy, potential energy, is equal to 2 times 1/2 kx squared. Here it talks about a different kind of energy. It's an energy due to a motion. For example, the resistance we talked about the last time. There's air friction. Suppose the force is proportional to the friction in air or in water is proportional to velocity. The friction matter is an extremely complicated thing. It depends on the shape of the body, and it depends on the property of the liquid or the gas. So this is just purely a hypothesis. If the velocity, if the air friction is proportional to the velocity, the question is how about the power? If that is the case, force is proportional to V. Power is F dot V. And is proportional to V squared. So therefore, if V increases by a factor of 2, the power increases by a factor of 4. But this is in general not necessarily correct. It also depends on what the velocity is. You all know that if an airplane flies too fast, it could become supersonic, and when it becomes supersonic, it's a completely different game. So the air resistance or water resistance is an extremely complicated matter. This is just an exercise. Now let us go back to our old friend, the swing. We have talked about a swing, so let's say there are two forces on the swing, on the object, and one is this force, the other is the tension on the rope. Now this you can resolve into two. So what is the force, total force on body in the direction of in the direction perpendicular in the tangent direction, namely in this direction. This force T does not have a component in that direction, and the mg has this component which is not in that direction, but there is a component in here, and since this is theta, so it's mg sine theta. However, for theta increasing, it goes this way, so there's a negative sign. So total force on body in the tangent direction is equal to minus g sine theta. Now, we had a formula last time. What I'm discussing, we already did last time, so I'm just repeating it. We had a formula for a body moving this way where r is a constant. The swing motion r is a constant. Then the acceleration in the tangent direction, in the theta increasing direction, is r theta double dot. Therefore, r theta double dot times m, that's m times the acceleration, that is equal to minus mg sine theta. We already had this formula last time, so therefore theta double dot is equal to minus g over r sine theta. This is the force equation. This is the equation that we obtained by using the force, and it contains the second derivative with respect to time. Thank you. Now instead of that, let us write down the energy equation. Energy equation says the kinetic energy, the particle is moving, it has only a velocity along the tangent direction, which is r theta dot. So therefore kinetic energy is equal to 1/2 of m theta dot, m r theta dot squared. And potential energy, potential energy is this is theta, this is r. So let us calculate what is, let's take this point to be the 0 for z. So what is this distance? Is equal to mg times this distance. We take this to be origin. So it's equal to r minus r cosine theta. So the energy equation says 1/2 m r squared theta dot squared plus mg r 1 minus cosine theta is equal to a constant, is equal to total energy. So I got 1/2 of theta dot squared plus g over r if I divide this by m and divide this by r squared d over times 1 minus cosine theta is equal to e divided by m r squared, which is a constant. This is the energy equation. This equation is the same as this equation. If I take the derivative, I immediately get that equation. Then you can do this as an exercise. So that explicitly shows that this energy equation is an integrated form of the force equation. All the rest are constants. So let us write it this way. We move everybody on the right hand side. So it becomes a plus b cosine theta. A is a numerical constant, b is a numerical constant. Now suppose the swing is such that its velocity is 0 when it reaches the top. Let's call that point theta 0. Suppose at this point theta 0, if theta dot is equal to 0 when theta is equal to theta 0. Theta is 0 is the value of theta where the swing stops. So that condition is theta dot equal to 0 when theta is 0. So I substitute that in there, then I get 0 is equal to a plus b cosine theta 0. I solve that for a, so therefore I get theta dot squared is equal to b times cosine theta minus cosine theta 0. This you can write as a differential equation. d theta dt is equal to square root of b times square root of cosine theta minus cosine theta 0. I move that, so I get d theta over square root of cosine theta minus cosine theta 0 is equal to square root of b integral dt, which is equal to square root of b times t minus a constant. This you can find in I don't know whether it's in Appendix E, but this is a standard integral. However, this standard integral is not in terms of a function which is well known. So now let us do an approximation. We do an approximation by assuming theta a small oscillation. In other words, like a 钟摆，钟的这个摆是一个 small oscillation. Mathematically, it means theta is small. Small compared to what? Small compared to radian 1. 1是一个 radian， 一个 radian 差不多是60度，所以比如说是 theta 是5度 ，theta 不超过5度。那么在这种情形之下呢，这个你可以把这个 formula 给改一下。你比如说我们现在来 用的 force equation。force equation 就变成 theta double dot 等于 minus g over sin theta。对，我照抄刚才。假如 theta 是 small 的话，你可以 expand theta into a power series, so it becomes minus g over r theta, because sin theta is equal. The formula is sin theta. 我们上回这个 formula 你们记住 ，sin theta is equal to minus theta cube over 6 plus theta fifth over 5 factorial minus这个 formula is pretty good。第一样，这个 1/6 也是一个小的数目，然后这个是 cube， 所以比这个 theta 小了 theta square 倍。假如 theta 是1/10，那 theta square 就是100%，再被6就是1 over 600，所以这个theta 在小的时候 ，this is a very good approximation. If that is the case, we have an equation 是 theta double dot 等于个 constant times theta。这个 equation 是什么样子的 function？ 连 differentiate 2次就回到它自己有一个 minus sign。Anybody? It's a sinusoidal function. Sinusoidal 就是一个 sine 或者一个 cosine。你把 sine 一 differentiate 就变成 cosine， 你再 differentiate 就变成负的 sine， 所以真的是原来一个 cosine 你 differentiate 就变成负的 sine， 你再 differentiate 就变成负的 cosine， 所以不管是 sine 或者 cosine， 或者是 linear combination， 你 a cosine theta plus b sin theta， 你连 differentiate 2次就变成了负的原来的，所以这是一个 typical 的，所以 theta 等于 sinusoid 等于 a cosine theta。这个 a 跟后头的 a 没关系啊，这你叫 a1 加上 b1 sin theta。刚才这个是用 force equation， 咱们来看看这 energy， 在这个 approximation 里头。这 energy 刚才我们已经写出来了，这 potential energy 是等于 G 是等于 mg r 1 minus cosine theta。这是刚才是从就是我从 the bottom part 最低点做0，那么这就是 mg z。可是 cosine theta 呢，你要把它好，我们刚才有 sin theta， 这个 cosine theta 有 similar formula， cosine theta 等于1 minus theta square over 2 plus theta fourth over 24减。我为什么记得这个 formula？ 你来，这些 formula 都是 come from 一个 exponential formula of e to the I theta。e to the I theta， 我们等会儿再回到这一点啊。Anyway， 你把这个 mgr 1 minus cosine theta 呢，就变成 theta square over 2。approximately。一个 potential energy 是等于这个 quadratic， 这跟刚才那个 spring 完全一样。那 spring 的 velocity， spring 的时候它的 kinetic energy 是 x dot squared， 它的 potential energy 是 proportional to x squared。 现在 kinetic energy 是 proportional theta dot squared， potential energy 是 proportional theta squared， 所以这个 mathematics 完全是一样的。这种 mathematics 呢是 typically 是一个 sinusoidal， 因为如果这 potential energy 是这样子的话，它的 derivative 就变成了那个 force law。关于这一点啊，我要再比较详细的 discuss 一下。那我们 discuss 另外一个问题，一个兼容的问题，是一个 slide，a complicated slide。这是 x axis， 我现在有一个滑梯，这滑梯是随便怎么样。Let us consider a frictionless slide. So you have a body here， 它在这上面 move 来。那么它有一个 kinetic energy， 它有一个 potential energy。我刚才讲过了，这个 z 我可以随便取什么地方是 origin。那么我把这个 energy equation 写下来，那就是这 potential 的不，这不应该，这是 mgz，OK，mgz， 可是这 z 呢是一个 function of v， 这 z 啊是一个 function of x。这个书上把这个叫做 u of x， 所以这个图呢，也就是这 u of x as a function of x。这种样子问题在物理里常常有，所以我们虽然 talked about 是一个 slide，but it actually works in general。对不起，你等我想想。I made a mistake。不能当做是个 slide， 因为 slide 这个 particle， 你们忘记掉我刚才讲的这个。是这样， 我要talk about 是一个 general potential energy， 可是我在昨天晚上在 prepare 的时候，说是这就像一个 slide， 我刚才讲了一半，知道这是不对的，所以你忘记掉我刚才讲的这个 slide， 所以我们现在从开始。我们刚才讲了一个 string， 这个 string 它的 energy 是 1/2 kx squared。可是，比如说是你这 string 不是一个regular 的 string 它的 energy 就不见得是那么样子的。那么 as a matter of fact， 一个 real string 它的 energy 也不是 strictly 是 1/2 of kx squared。所以呢，我现在就 talk about 这个 general 的等于一个general potential energy。Let us assume 这是 x 是这 displacement， 然后这个 force 是一个as a function of x。是不是能做到这样子的话呢？一定要做是可以做到的。不，这个通常的这个 spring 你把它这样子的话，它第一样它不会拱来拱去的。But for 我们现在的 discussion，let us assume you can do this。那么在这前提之下，我们要说是它这个 total energy 就是 u of x 加上 1/2 of m dx dt squared 是等于一个 constant， 这是它的 energy equation。假如我把这 equation 拿来，就是 take the derivative with respect to time， ddt of u of x 是什么呢？是 du dx times dx dt。这个 differential 就变成 m dx dt times d square x dt squared。把 dx dt 消掉，就得出来 m d square x dt squared 等于负的 du dx。这是我现在要的这个方式。这是什么意思呢？ m 乘上 d square x dt squared 当然是 force， 所以这代表 force 是等于这个。in other words force 是等于负的 du dx， 这是我也要的。所以 repeat， 假如有一个 spring 或者是有个 complicated gadget， 它的这个 potential energy 是这样的。那么在这个 spring 在每一个时间呢，比如说它在这个地方，它的 force 就是负的 du dx， 在这儿也是 du dx。比如说，假如这个 potential energy 是 1/2 kx squared， 那你把它 take a derivative down to the minus kx， 就是真正我们从前来的。换句话说，这只是 more general 的 case。刚才我讲这个有没有疑问？好了，这一 understand 以后，我就回到刚才的图，那就是代表说是在这一点 du dx 等于0，所以在这一点它就不动，就是没有 force， 在这点也是没有 force， 在这点没有 force， 所以这些 points where du dx is equal to 0， 在那没 force， 那个叫做 equilibrium point。 这个 point 叫做一个 stable equilibrium， 这个 point 叫做 unstable equilibrium。当然了，因为这为什么叫 unstable equilibrium？ 你在那稍微动一动，前后动一动，比如说是你动到这儿，它的 slope 是正的，可是前面有个负号，所以这个 force 是把它向后推。要到这一点的话呢，它 du dx 是 negative， 可是负的 du dx 是 positive， 所以就把它向里头 push， 所以总而言之在这附近呢就互相 oscillate。可是在这一点的话呢，你要稍微deviate一点，它就一直走过去了。所以这是 unstable equilibrium， 这是 stable equilibrium。 But more than that， 就是你如果这个 u 是这样的，你不管别的是怎么的，我们刚才讲了when it's displaced slightly to the right, it will push back to the left and vice versa. Now a curve around a point near a stable equilibrium, the U curve can be approximated by a parabola. 为什么呢？你在这附近你把它 expand 起来好了，通常一个 smooth 的 curve你都可以 expand 成一个 power series。 如果拿这点做0，做 x 等于0，那你就可以 expand 成一个 power series， 就是 a plus bx plus cx square plus dx 来的。假如在那点的 slope 是等于0的话，那个 bx 项必须要等于0，因为它的 derivative 在 x 等于0的时候就是 b， 所以那项必须等于0。所以 start with the quadratic term。 In other words， 在这个附近啊，这个 u 最容易有一个现象，就是一个 a 加上 b x delta x 的 square。 这个 constant 没什么大重要性。如果它的在那个附近，你如果把这后的这些都 eliminate 都 neglect 掉的话， then you get the potential energy is proportional to delta x squared, and therefore its force is minus its derivative is proportional to x. So what's the conclusion? The conclusion is as long as you are near a equilibrium point, as long as the quadratic, this is called quadratic approximation, approximated by a parabola, is a quadratic approximation. As long as you can make a quadratic approximation, it's a sinusoidal wave because it's equivalent to a spring. The curve can be approximated. Therefore, the motion is like a spring vibration. I.e., it is sinusoidal. I only want to say all small vibrations are approximately sinusoidal. That is why the spring motion is so important. For a real spring, the motion is very well described by a sinusoidal wave. But what I'm saying is that for all small vibrations, a good approximation is sinusoidal. That is the reason why in physics sinusoidal motions are so important. Okay, have a good long holiday, and we'll be back after the holidays. Oh, Saturday the 9th, Professor Ran or Professor An will take over for 1 hour.